Welcome, ladies and gentlemen, to another lovely episode of Dave Does Math from Home. I'm pretty excited about this one. This one is a good section. I like this one a lot. Today we're talking about rational expressions. Rational expressions are pretty fun because they're sort of like the other half of dividing polynomials. I mentioned in the last couple of videos that we were going to talk about how to divide polynomials. No, I guess in P4 I talked about, because in P4 was adding, subtracting, multiplying polynomials, and I said division was for later. We sort of talked about division in P5 because we talked about how to factor them, how to break them into different multiplying pieces, but we didn't actually divide anything. We just talked about what their factors are. This is a section where we're going to talk about what happens when you actually divide polynomials by other polynomials, and that is essentially what a rational expression is. A rational expression is essentially just a polynomial, or it's not a polynomial. Sorry. I almost said it was a polynomial made out of fractions, but that's not it. It's a fraction made out of polynomials. So all of the standard rules of fractions apply. Like if you want to add two of them together, you need a common denominator. If you want to divide two, you have to change that to multiplication and multiply by the reciprocal. Keep, change, flip, I think some people call it. All the rules of fractions apply because these are fractions, but they're made out of polynomials instead of being made out of numbers. And that means that all the rules of polynomials apply as well. So we're not going to be dealing, the things we're dealing with, they won't have any square roots. They won't have any weird nonsense like sines, cosines, logarithms, none of that. There won't be any goofy exponents, but there will be a chunk on the bottom that's a polynomial because it's a fraction. Fractions have denominators. So we might look at things like 5 over x minus 3. This is a rational expression. 5 isn't much of a polynomial to put on top, but it technically counts as a polynomial. More exciting things might look like x squared minus 9x plus 8 over x squared minus 5x minus 24. This is a pretty characteristic rational function. So when we first started talking about polynomials and we defined what a polynomial was, one of the reasons that we talked about that definition, one of the reasons we talked about for that definition was that we wanted these things to be simple and smooth and continuous and nice and well behaved. And if we want things to be smooth and continuous and nice and well behaved, we have to keep variables out of denominators. Because sometimes when you put variables in denominators, that makes those denominators equal 0, and then you're in big trouble because then you're dividing by 0 and that's no good. So that's going to be a thing in this section. We're going to have to deal with that. We're going to get some rational expressions like this, and we're going to need to determine what the domain restrictions are. So because there's variables in the denominator here, there's going to be certain x values that make the whole denominator equal to 0, and those x values are not allowed. So some of the questions we're going to encounter on the homework are going to be about how to make the denominator not 0. So for something like this, I think it's pretty clear x can't be 3. There's not a lot to that. X can't be 3. That's it. For something like this, we're going to have to do some work to figure out what the domain restrictions are. And the work we're going to have to do for these is factoring. The section on rational functions comes after the section on factoring polynomials because factoring polynomials is about 70% of what we're going to be doing in this section. All of the math, like finding domain restrictions, factoring. Finding common denominators, factoring. Multiplying polynomials together, factoring. It's all factoring. It's just factoring all the way down. Which is why P5 went well. So now we're masters of factoring and we can do this stuff easily. If we want to factor this thing, I think it's going to look like -8, -1 on top, or x minus 8, x minus 1 on top. The bottom, I think, is going to look something like multiplies to -4 and adds to -5, so that's probably -8 and +3. X minus 8, x plus 3. So this is what we're working with as the factored version of this polynomial. One of the things that we're going to see happen in this section a lot is that things will cancel. I promised you a section about dividing polynomials, and this isn't exactly it, but this is close. We can divide these polynomials, and there's not a lot we can do. Like, this is something divided by a polynomial. There's not much we can do to simplify this. You kind of just have to look at this and acknowledge, like, yep, something got divided by a polynomial. Cool. It's all right. Okay. And you're just sort of done. Sometimes when you see these things divided like this, you will be able to simplify. But you have to be very, very careful. One of the common mistakes I see students try to make with these things is that students will try and cancel terms from this. Like, students will look at this and be like, well, there's an x squared and an x squared, so we can cancel those. That doesn't work. These relationships, these terms, the relationship of these terms to the rest of this is addition and subtraction. Like, that's the relationship between the x squared and the 9x, that's subtraction. Between the x squared and the 8, that's addition, like, etc. You cannot cancel addition and subtraction operations with division. That doesn't work. You can cancel multiplication relationships with division, and that's one of the big reasons that we want to factor things. Because once it's factored, we have an x minus 8 factor and an x minus 8 factor on the top and the bottom. Factors cancel with division. Terms do not. You can't cancel these x squareds. Canceling these x squareds is like looking at something like 24 over 27 and being like, oh, I'll cancel the 2's. It doesn't work. But factors do cancel. This is no bueno. If you want to factor 24 over 27, you could pull a 3 out of each and say that this is 8 times 3 and this is 9 times 3, and now you can cancel the 3's because this relationship is multiplicative and division cancels that. This relationship is multiplicative, division cancels that. But I'm getting a little bit ahead of myself. Let me go back to domain restrictions. The reason we factored this thing in the first place is because we wanted to look at the domain restrictions. And with the domain restrictions we have an x minus 8 term, so x can't be 8. That would make the denominator equal to 0. Well, that would make this piece equal to 0, and then it doesn't matter what this is. It's being multiplied by 0, so the whole denominator is 0. That's why factoring things is very convenient. So x can't be 8 because of this. X can't be -3 because of this. Those are the domain restrictions sort of imposed by this thing, this denominator on the bottom. Here's what's really weird about canceling factors from the top and bottom. We can cancel these. The x minus 8's and the x minus 8's, those can go away. We can say that this whole rational expression is the same as x minus 1 over x plus 3. The x minus 8's can go away. The domain restriction stays. X still can't equal 8 or -3. Here's why the domain restriction stays. If you start plugging numbers into this, like if you take, for example, x equals 9. When you plug x equals 9 into this, you'll get 1 and 1. Those cancel. That's fine. If you plug in x equals 20, this piece is 12. That's 12. That cancels. That's fine. If you plug x equals 1,000,009, this term is 1,000,001, this term is 1,000,001, those cancel, that's fine. You can plug in any value of x, and these things will cancel each other out because they will be the same number, except x equals 8. If you try to plug x equals 8 into this thing, then you get 0 over 0, and that does not cancel. 0 over 0 is not something that you can just say it cancels. It's the same number, it cancels, it's done, move on. It doesn't work. 0 over 0 is indeterminate, which is, it's like undefined but worse. 0 over 0 is indeterminate, so there's nothing you can do with that if you get the 0 over 0. So in order to cancel these things only cancel if you say x can't be 8. As long as x is literally anything else except 8, these things cancel and you can make them go away. But because they only cancel if you say x can't be 8, then after you cancel them, you have to keep saying x can't be 8. So that's sort of a long explanation. The short version is, don't cancel terms, cancel factors, the domain restrictions from those factors stay. So that's domain restrictions and also canceling. The other thing to keep in mind about domain restrictions is, turns into a point of confusion for many students at least once in their mathematical career. The top doesn't matter. Like, lots of students, I think, in the past have looked at something like this and told me x can't be 1. No, that's fine. X can be 1. If the numerator of a fraction is 0, that's fine. That's not a problem. The numerators can be 0. It's the denominators that cannot be. So if this factors into x minus 8 and x plus 3 on the bottom, then x can't be 8 and x can't be negative 3. And even after that cancels, the domain restriction stays. So that's rational functions. That, I think, is a pretty comprehensive introduction to what they are. But most of this section is about doing things to them. So now that we have a pretty good handle on what rational functions are, it's time to start talking about how to add, subtract, multiply, and divide rational expressions. That's the goal for the rest of this section. And I would like to start a new video to talk about that, so stay tuned.